All right, in this video, we're going to look at another rate of change, and we're going to talk a little bit about notation as well. So this says let a equal pi r squared be the area of a circle of radii. That should say radius, not radii. Missing yes. Of radius r. Compute dA dr. So let's do that first. So dA dr. Remember, pi is a constant, so we just use the power rule. So we bring down the 2, it's 2 pi r. And it says if r is in centimeters, what are the units for dA dr? Well, dA is a change in area, and dr is a change in the radius. So it would be centimeters squared per centimeter. Another way you can think of that is if we were to graph the area as a function of the radius, right? Then the derivative would be slopes of tangent lines. So again, if this is the radius axis and this is the area axis, if we graph pi r squared, we're essentially graphing a parabola at the origin that looks like this, not a straight line. There we go. It's a little odd looking parabola. That gets the job done though. Right, so any slope of any tangent line would have units. Let's just say we have a tangent line there. The slope of this line here, assuming the radius is in centimeters and the area would therefore have unit centimeters squared, then we can see a change in y is centimeters squared per centimeter. Okay, so those units make sense. Compute dA dr at r equals 2 and r equals 5. So when you're evaluating using this notation, it's typically common to draw a vertical bar and then write the value like this. So dA dr when r is 2 is going to be 2 pi r. It's 2 pi times 2, which is 4 pi. And again, the units are centimeters squared per centimeter. And when r is 5, we get dA dr when r is 5 equals 2 times pi times 5, which is 10 pi centimeters squared per centimeter. I think the other thing I should have mentioned is you notice that dA dr is is 2 pi r, which is the formula for circumference. And that should make some sense to you because when a circle is growing, right, at any instant, its area is increasing. Well, in the limit, infinitesimally, it's increasing by the circumference amount, right? You can imagine just every instant layers of circumference kind of accumulating. So it makes sense that that's the rate of change, right? And typically, when this is trying to be explained, you draw a different circle around it. You just note that the small change in the area is. I'm going to abandon that project there, but the idea is that at any given instant, it's like you're increasing your area by rings of circumference. And then it says, why is dA dr larger at r equals 5? Well, I think I'm just going to indicate that this makes sense because each small change in radius let's call that change in r, that's going to produce a larger change in area as r increases. Now we can see that by the graph up here, right? Clearly, as the radius grows, the slopes get steeper, right? So the rate of change is greater. But down here, you can also see it visually looking at the circle, right? Every 1 inch increase in radius when r is 5 is producing more area than when R is 2, just because you can see that that pink ring is clearly much bigger and is producing more area than the one at R equals 2. So this is just a little look at a rate of change involving a circle and also some new notation.